All right. Hi. So today we're gonna discuss what? What are we gonna discuss? Do you remember what are we gonna discuss? We're gonna discuss the design of the infinite impulse response filters, right? In the last class, we saw that what infinite impulse response filters are. So these are essentially filters that have an infinite impulse response, and the reason they have the infinite impulse response is primarily because of the feedback loop. All right. Okay. Now, what we're gonna do today, we're gonna see how we design these infinite impulse response filters, and more specifically, we'll see how we're gonna design them using the bilinear transformation design. Right? And I guess you guys have this problem of things flickering on the screen, so now it should not be there. Oh, yeah. Okay. Right. So let's look at a couple of slides for that. And I say display settings and duplicate the slideshow over here. Okay. Now, it essentially has these three stages, right? So you first start with the digital filter design specifications, right? By the way, just to give you some history, why do we do this? Why do we use bilinear transformation or to design the infinite impulse response filters? Some history is like when digital filters came along, the analog filters were pretty mature, right? So the theory for the analog filters was pretty mature until that time, right? So what we said, okay, can we use the existing knowledge about these analog filters to design digital filters, right? So we came up with this bilinear transformation design method, which uses the stuff that we have for the analog filter design and converts that to the digital filter design. Right? And how do we do that? We start with the design specifications for a digital filter, right? And then we do some transformation to convert them to the equivalent analog filter, right? To the convert them to the equivalent design of the analog filters. And then once we have the specifications for the analog filter, we take a low pass prototype filter and convert it into a filter of the specifications that we get at this stage, right? And then once we have the filter of certain frequency specifications that we came up over here in this stage, that means we have the transfer function of the corresponding analog filter, then we apply this bilinear transformation to design the digital filter, right? To convert the transfer function of the analog filter to that of the digital filter transfer function. So again, we start with the specifications of a digital filter. We apply some sort of transformation to get the specifications of the corresponding analog filter, and once we have the specification of the corresponding analog filter, we excuse me, we take a low pass prototype analog filter, convert this into an analog filter of these specifications. Once we have the corresponding analog filter, then for the specification that we got in this step, then we apply a bilinear transformation to get the specifications or to get the transfer function of the digital filter. So far so good, right? So this is the entire setup. What we will do here, we will start with step number 2, right? So in step number 2, we assume that we have the specifications of an analog filter, but we use the prototype low pass filter to convert it into an analog filter of the specification that we have here. Okay, and what do I mean from that? When we talk about a low pass prototype filter, what we mean to say is like we have some analog filter whose cutoff frequency is 1 radians per second, right? So for that reason, we call it a prototype filter. Now, these prototype filters can be of different types, right? What we will do, we will take the, let me just go to here. Yeah, so we will take the prototype filter, which is a Butterworth filter, right? So we'll take a Butterworth. low pass prototype filter, and its good morning, and its transfer function looks something like this, equals 1 over s plus 1. And we can verify that this indeed is a prototype filter by showing that its cutoff frequency is at 1 radians per second, right? Now, how we can do that? By the way, if you know the transfer function of, I'm sorry, I don't know why this flickering is happening today. It was not happening last time, for the screen. But anyways, so I'm recording the lecture as well, right? So if you have the transfer function in the S domain, you want to get the frequency response, what do you do? Yeah, exactly. So you just evaluate the transfer function on the vertical axis, right? And let me use the variable nu for the frequency right over here. So what I can do, I can just substitute s with j nu, right, to evaluate the filter on the transfer function on the vertical axis. So I will have this guy, right? And this is 1 over j nu plus 1, right? Or 1 over 1 plus j nu, right? And then I can find its magnitude frequency response. And how do we do that? By the way, whenever you have something, in the denominator, the first, something complex in the denominator, first step is you can rationalize the denominator. That means you multiply and divide by the complex conjugate of the denominator, right? And then you can do the simplification. You will find out that its magnitude response looks something like 1 over 1 plus nu square root, right? And then you can verify that what kind of filter is this, and how you can verify that. We can evaluate it let's say at the frequency 0 radians per second, right? If we do that, what would be the magnitude response at this particular frequency? It's going to be 1 over 1 plus 0 square root is going to be 1, right? And that is what we expect from a low pass filter, that for lower frequencies, its response is 1, right? Or close to 1. Let's say for nu equals 1 radians per second, right? So for this particular frequency, it's going to be 1 over 1 plus 1 square root, which is 1 over square root 2, or the 3 decibel point from the vertical axis, right? So compared to the highest response, and this is essentially the cutoff frequency for the case of Butterworth filters, right? That means this one is essentially the cutoff frequency. And then you can also verify that as nu goes to infinity, right, what happens to the gain? The gain goes to 0, right? Because when you have something that is increasingly bigger and bigger and bigger, so the whole thing will become smaller and smaller. Okay, so this indeed is a low pass prototype filter, right? And more specifically, this is a Butterworth low pass prototype filter, right? And the order of this filter is 1. Yeah. Now there can be low pass prototype filter of higher orders as well. Like for example, if you talk about order 2, so a Butterworth low pass prototype filter will have the transfer function that looks like 1 over s square plus 1.4142s plus 1. Of order 3, it's going to be 1 over s cube plus 2s square plus 2s plus 1. And as we increase the order, what happens? Yeah, so the roll off of the filter becomes sharper and sharper, right? So if we need like a smaller transition band, so we just have use the prototype filter of a higher order. Yes. Okay, good point. So that we discussed in the very beginning of the class. When we started developing the digital filters, the theory for analog filters were already pretty mature, right? So the idea was, can we use that knowledge to make digital filters, right? So for that, we are essentially dealing with bilinear transform design, right? So what we do, we take the digital filter, start with digital filter design specifications. We convert them to an equivalent analog filter design specifications, right? Why do we do that? We will see that later, right? Because we will see, let's suppose a cutoff frequency of 10 hertz is not the same in the case of digital filter, right, compared to an analog filter. So we convert it into the corresponding analog frequencies. Then we take a low pass prototype filter and we convert it into the filter specifications that we get in this step, right? And then once we have the corresponding analog filter, we apply bilinear transformation to get the digital filter, right? So right now we are focusing on this one, right? We're focusing on the design of or the if you know the analog filter design specifications, how can we use a prototype low pass filter to convert it into the corresponding analog filter of these design specifications. Okay, so for up till now we have verified that this, for example, particular low pass prototype filter has a cutoff frequency of 1 radians per second. So this is a prototype filter, right? So we'll use these filters as an example, right, to see how we can convert them into, let's suppose, another low pass filter, another high pass filter, and so on and so forth. Now, we'll use this as an example, which is of order 1, right? But the thing is, the same kind of explanation applies for order 2 filters, order 3 filters, and so on and so forth. Clear? So far, so good? All right. Now we established that this is a prototype low pass filter, right? Okay. Now, my claim is that if I replace S with S over omega C, where omega C is the cutoff frequency, I convert the same transfer function into the transfer function of a low pass filter with a cutoff frequency of omega C radians per second. So basically what I'm doing is like I'm scaling the frequency axis. Yeah. So if I start with the low pass prototype filter, right, whose cutoff frequency is 1 radians per second, I just replace it with S over omega C. The new cutoff frequency is going to be omega C radians per second. Okay. So that is our claim. And let's verify this particular claim. So we'll, yes.
What's V in this case?
What in this case?
JV.
It's not V, it's nu. It's the frequency axis. Right? So sometimes we use nu for the frequency axis, or like sometimes use omega for the frequency axis. Um, the reason we use nu here is like just to show that this is for a filter whose cutoff frequency is 1 radians per second. Right?
How do you pronounce it, Professor?
Nu, nu, Neu, right? It feels cool as well, and if you want to write it, it's like this, right? So it's like a V, but V is having a lot of winds coming in, right? So it got distorted to V, right? New, right? So that is how they got the new. I just made it up. Honest to God, right? I have no idea about it. I'm kidding. I mean, this is a Greek letter, right? Yeah. We use these Greek letters. They sound cool as well. It's not W, it's omega, right? Omega sounds cool. It's a small omega, right? The big omega is like this, right? We also use it for ohms, right? Why? Because it looks cool, right? We could also have used just OH for ohms, right? But then whenever you say like, the resistor is 3 ohms, you said 3 O. No, it doesn't make sense, right? 3 O. I messed it, right? Coming back. This is being recorded. I should control my jokes. Coming back. Right? So my claim is if I replace S with S over omega C, right, I'll get another low pass filter whose cutoff frequency is now omega C radians per second, right? So let's verify this claim. So let's say conversion to a low pass filter of cutoff frequency, which is omega c, right? So I have hp of s, which is 1 over s plus 1, right? I just replace it s with s over omega c. I get, let's say I call it HLP of s. This is just 1 over, in place of s, I just replace it with s over omega c. And then after doing some simplifications, this is going to be omega c over s plus omega c. So let's verify that this omega c guy, this HLPFS is indeed a low pass filter of cutoff frequency omega c radians per second, right? Okay. Now again, to get the frequency response from this transfer function, what do? We just replace s with j omega, right? So to get the frequency response, we just replace s with j omega. So then we will have HLP of j omega. Then we have omega c over j omega plus omega c, right? Or I can just simplify this. This can be also be written as 1 over j omega over omega c plus 1. So I just take omega c common from both numerator and denominator. Yeah. So far so good. All right. Now, if I want to find its magnitude response, right? So this, by the way, can also be written as 1 over 1 plus j omega over omega c, right? So I can just rationalize the denominator, multiply and divide by its conjugate, do the simplifications. So I'll find the magnitude frequency response as 1 over 1 plus omega over omega c squared root. So this is the magnitude frequency response. Again, how can we get it? I just multiply and divide by 1 minus j omega over omega c, right? And I do the simplifications. I got the real part and imaginary part. I sum and square the real and imaginary parts, do some simplifications, so I'll get this relationship. Okay. Now, what do we want the gain to be for the frequency 0 radians per seconds? 1. Want the gain to be 1, right? So let's see for omega equals 0, right? So the gain is going to be 1 over 1 plus 0 squared, right? That's just 1. All right. At omega equals omega c, the gain is going to be 1 over 1 plus omega c over omega c squared, right? This is going to be just 1 over square root 2, which is essentially the 3 decibel point, right? That means this is the indeed the cutoff frequency. And then we can see that as omega goes to infinity, what happens is like you have some term over here, 1 plus infinity over something, right? Some big number over something. So this whole thing becomes bigger and bigger. The denominator becomes bigger and bigger. So as omega goes to infinity, the gain goes to 0, right? So this transformation indeed converts this low pass priority filter into another low pass filter of the cutoff frequency omega c radians per second. Clear? Questions? Problems? Complaints? All is well. Good. All right. Next up is conversion into high pass filter. So you can convert the same low pass filter prototype into a high pass filter by just replacing s with omega c over s, right? So again, it's like kind of like rescaling the the frequency axis like in a different way, right? So what it will do, it will just convert it into a high pass filter of the cutoff frequency omega c radians per second, and you can follow the same kind of derivation that we did earlier to verify that this is the case. Okay, clear? Clear, clear. All right, good. Same idea. You can just replace S with S square plus omega naught square over SW to convert it into a band pass filter, right? What is this omega naught? This omega naught is essentially the geometric mean of the lower and higher cutoff frequencies, radians per seconds, right? And this W is essentially the bandwidth of the filter. So it's a band pass filter, right? So it lets certain frequencies to pass through and tries to get rid of the other frequencies. Clear? Clear? Yeah. Okay. Same idea. You can convert it into band stop filter by just flipping it again, right? So you just replace S with SW over S squared plus omega naught square. Omega naught is essentially the geometric mean of the lower and higher cutoff frequencies, and W is like the bandwidth of the frequency that you want to get rid of. Okay, centered at omega naught. Okay, let's do an example to see. Let's suppose we start with a low pass Porter filter and we convert it into a high pass filter or a band pass filter, right, of the desired specifications. Questions at this point? All good? Sure? Sure. Okay, good. Okay. So, or example, no, this is example, not example, right? It's different. Example. All right. Given a low pass Purdy filter, which is HP of S equals 1 over S plus 1 fine. What do we do? Determine a high pass filter with cutoff frequency of 40 radians per second. B, a band pass filter with cutoff frequency of sorry, not cutoff frequency, with a center frequency of 10 radians per seconds and bandwidth of 20 radians per seconds. All right, so let's do part A. So we know that if we have low pass Purdy filter, we can convert it into high pass filter by replacing S with omega C over S. But this omega C is the cutoff frequency in radians per seconds. So let's do that. So here the cutoff frequency omega C is 40 radians per seconds. That implies that we need to replace S with omega C over S. That means S with 40 over S. So we start with the Purdy filter and we replace S with omega C over S, in this case 40 over S. So we have 1 over 40 over S plus 1 and then you can simplify this saying that this guy is S over S plus 40. Clear? All good? Okay. Let's look at part B. Now, for a band pass filter, the transformation looks like this. We just replace S with S square plus omega naught square over SW, where omega naught is the center frequency and W is the bandwidth, right? So the transformation, we need to replace S with S square plus omega naught square, S square plus omega naught square over SW. And in this case, omega naught is, what is the omega naught here? It's the center frequency, right? 10, 10 radians per second, right? This is 10 radians per second, and W, the bandwidth, is 20 radians per second. That means all what I need to do is I replace S with S square plus 10 square over 20S. What is 10 square? Sure? Yeah, sure. Okay. So it's this one, right? So all what I need to do, I take my low pass prototype filter, I just replace S with S square plus 100 over 20S to get my band pass filter, which is 1 over, again in place of S, I'm just replacing S square plus 100 over 20S plus 1, right? And I can take the LCM. This is going to be 1 over S square plus 100 plus 20S over 20S, right? This 20S will go up, and then you have the transfer function, which is 20S over S square plus 20S plus 100. So this indeed is the transfer function of the corresponding bandpass filter. Clear? Any questions? All good? Okay. Now, if you want to plot the response or the frequency response, for example, for a filter with these, that has like this transfer function or, this transfer function, right? So you can do that by the function frac s in MATLAB, right? Where you plug in like B, A, and W. So B is essentially the vector contains the numerator coefficients of the transfer function. A is the vector containing the denominator coefficients of transfer function. W is the vector containing the specified analog frequency points, right, at which you want to compute the frequency response. And H will be the output vector, or like the result of the computation of the frequency response at those frequencies. Okay. By the way, when you talk about this B, A, and S, we're talking about the transfer function in the standard form, right? Like for example, in the case of the Z transforms, we had like B naught plus B1 Z to the power minus 1 and so on and so forth, right? So here you just can convert the positive powers and negative powers. The corresponding transfer function in the standard form is going to be, let's suppose this 1 plus 20 S2 minus 1 plus 100 S2 minus 2, right? And in the numerator, you'll have 20 times 20S to the power minus 1, right? And then from here, you can compute the numerator coefficients and denominator coefficients, right? Sorry? It's the same, but for example, the case of B, which is the numerator coefficients, right? You will have the coefficient which is 1 and 20, because you had, sorry, not 1, 0 and 20, because you have 0 plus this, right? Yeah. And for the case of A, you would have 1, 20, and 100. Clear? Questions? All good? Okay. So we did the examples, and if you plot the transfer functions like magnitude responses. For example, for the case of the high pass filter, the magnitude frequency response looks like this, right? For the case of the band pass filter, the magnitude frequency response looks like this. You can see, it is centered at 10 radians per second, and the bandwidth is around 20 radians per second. Clear? Good. All right. So let me just discard this. So this concludes the first part of the bilinear transformation design, right? Sorry, the second part, in which we know the analog filter specifications, and we use a prototype filter to convert to convert the prototype filter into the analog filter of the specifications we got in this step, right? So we are done with step number 2. Now we are going to see step number 3 and step number 1. Clear so far? Yeah? Okay. So let me just stop